Hear me all right? Yep. Okay, good. Hey, well, good morning, everyone. Nice crowd. I'm here to introduce our guest speaker today. Dr. Joannah Hinz is the Deputy Director of the Large Binocular Telescope Observatory, a facility of the Stewart Observatory at the University of Arizona and Associate Research Professor at the University of Arizona. He was previously a staff scientist at the MMT, which we can see up on top of the mountain from Green Valley. And MMT is a collaboration between the University of Arizona and the Smithsonian Institute. Dr. Hinz's research is centered on infrared observations of nearby galaxies using the Spitzer and Herschel telescope, among others, with interest in dust content and outer disk evolution. She received her Bachelor of Physics from MIT in 1995 and her PhD in astronomy from the U of A in 2003. So if you would, let's give her a big round of applause.
Well, I'm back. So as Steve said, I worked at the MMT Observatory for 12 years and I ran this lecture series for 5 of those. So it feels like coming home. So now I work at the Large Binocular Telescope Observatory. I just moved there in June, and so this is my very first lecture on this telescope. So what is the Large Binocular Telescope? It's actually exactly what it sounds like. It's a large telescope that looks out at the sky like a pair of binoculars with 2 8-meter mirrors on a single mount. I can try. If I had a shirt up here, that would be great. Okay, so we are located in the Pinaleno Mountains, which are near Safford. It's about a 3-hour, 15-minute drive from the Tucson area, so a little longer for you guys. It's a very high altitude site. So Whipple Observatory here, the MMT, that's at about a little over 8,000 feet. So the LBTO is over 10,000 feet. The site has exceptional seeing, but it also is very well known by the fact that mid-infrared observations and sub-millimeter observations are taken really well from that site because the water vapor in the atmosphere is pretty low given the high site and the dryness of this area. So its mission statement is discovery driven by innovation. It is a very unusual and innovative telescope, and we'll go into some details about that as well as some of the science that it does. So it's an international collaboration. Unlike the MMT, which has 2 partners, Arizona and Smithsonian, this one has multiple partners. So 25% of it belongs to Arizona, but that includes Arizona State and Northern Arizona University as well. 25% belongs to a number of institutions that are in Germany. 26% to Ohio State. To be honest, I don't know the details of 25 versus 26% and how that came about, but sometimes these things have to happen in order for projects to move forward with the 76 horses pulling them. And under Ohio State are Minnesota, Notre Dame, and the University of Virginia as well. And so all of those institutions are involved with the telescope from the beginning and remain in that now. At the end of 2025, the German contingent is moving on. They're building an extremely large telescope of their own, and they're putting their resources elsewhere. So if you would like to buy 25% of a telescope, I'm your girl. So I did not use the title that you were shown today. I didn't give that to Amy. Amy made that one up. And the reason I would never have used it is it's kind of a controversial statement, right? The world's largest optical telescope. Is it really the largest optical telescope? Well, I think we can rule out the ones that don't exist yet. What do you think? Because in this diagram, they're showing the hopes and dreams of your favorite astronomer, but we don't know that those will come to pass. And I'll probably say something controversial on every single slide. How many people think the NSF is going to get $500 million to build GMT this year? That's what I thought. How about any year? Okay, so we don't know about the future of these other telescopes. They would be bigger than the LBT, but we don't know how many of those extremely large telescopes will be built. So I crossed those out. So there are some single dish telescopes which are larger than 8 meters. So Keck telescope, for instance, is 10 meters, right? And the Hobby Everly in Texas, and the Gran Canaria telescope. Those are all in that, 8.5 to 10 meter range. So, but they only have one mirror, and we have two. So we're not the largest single dish. We're the largest two telescopes used together. Oh, you say, but there's Keck has two telescopes, but they stopped using them together some time ago. The VLT has 4 telescopes, which they do use together. They're not on a single mount. So now you know how many qualifiers. Oh, and then they're in the southern hemisphere. So if you put like 50 qualifiers on it, we're the biggest optical telescope on one mount. Okay. And that's what it looks like from the inside. This was as it was being built without any of the instruments and the other infrastructure. So from end to end, it's 23 meters across. So now we're looking at it sideways. And the two 8.2 meter mirrors are towards the bottom in the red, being held by red structure. And this setup is what makes LBT truly unique compared to other telescopes. So it has so many different configurations that can be used and so many ways to use the mirrors together separately. So if you were only using the primary mirrors and nothing else, you would still be able to use what we call the LBCs, the large binocular cameras. They're located up where it says LBC and there's a little arrow pointing. So you're just using the reflection from the primary mirror, and that's it. We still have those images. They're now 20 years old. They're still being used. Or you can use the swing arms and move those cameras out of the way and move a secondary mirror in on different swing arms. And you can reflect the light back down through the hole in the primary mirror, and you can have instruments on either side located underneath. Those are the orange cylinders that are towards the bottom. Right now we have there the MODS spectrographs, 2 optical spectrographs. Now you can use one of the spectrographs on one side and one of the LBCs on the other side. So you can swing in one LBC and you can swing out the LBC on the other side and swing in the secondary mirror and use MODS on the other side. And then there's many more choices. So you can also swing in a third mirror, a tertiary mirror if you want to, point the light into the center of the telescope. And we have a number of instruments there, most of which are infrared imagers and spectrographs. So you can use those in any configuration. So you can use LBC on one side and an infrared camera on the other. You can use MODS on one side. You can use MODS on both sides. So if you, in the middle of the night, have conditions that are changing very rapidly and it's very windy, and all of a sudden the conditions are terrible, and you cannot do the science that you really wanted to, you can, in the middle of the night, change the configuration of the telescope completely and choose something else that is better suited to the conditions that you have. So that's pretty unusual, and it takes about, depending on which configuration you want to change during the night, anywhere from 10 to 20 minutes to switch configurations. So you are going to lose that time because you cannot observe while you're doing that. But over the course of a whole night, it's not that much time, especially if you can basically optimize the observations that you want to do by doing that. The other very interesting thing that was developed partly at the MMT and then sort of refined at LBT are adaptive secondary mirrors. So now we're looking down on the telescope from the top. We have the big primary mirror. The secondaries are adaptive. That means they, in real time, are changed at the back in little fluctuations to try to correct for the atmospheric scene above the telescope. How do they do that? Well, they have a very thin mirror, and on the back of that mirror are over 600 little piston actuators, which are working to change and respond in real time to what's happening in the atmosphere. And in this way, you change a night of okay seeing, we call it, so okay conditions, to something really spectacular. Doesn't happen all the time because the weather's not great all the time, but when the conditions are stable and quite good, then you can use the adaptive secondaries to make them even better. How do we run this telescope? I just told you there were a bunch of institutions involved. How do we do the scheduling? So the way it's done right now is we have about 60 staff members on site. MMT has something like 20, 25 people. So bigger telescope, more complicated, bigger staff. It's scheduled on a semester basis. And the way that it works at the moment, and this has changed over the years, is that the staff of the telescope are actually the ones running the instruments and taking the data for the astronomers. The astronomers can be involved, they can be online, they can be at the telescope if they want to, but typically they're not the ones running the instrument. And each partner does things slightly differently. So those color-coded blocks belong to each partner institution. So that OSU is green and Arizona is typically purple. And each of the institutions has a night of, 5 to 7 nights in a block. And they all submit their targets. All of the astronomers who want to observe something at a time submit their targets. The staff review them, and then they're observed during these blocks. Now, here's my controversial, and there can't be anything controversial about this, right? But I'm going to say it anyway. So I think this is not the most optimal way to do things. I've only been here a few months, so of course I think I know everything and want to change everything. But I think the more efficient way to do this would be to put everybody in one giant block and have the staff have all of the targets for the whole semester in one block, which they then go through, and the top priority targets get observed every night, and we keep trying those top priority targets until we've gone through all of them. Then we go to the next range. So some telescopes do that. So Gemini does that. The MMT does that mostly. The LBT has not quite gotten there, and part of the reason is because you need buy-in from every single partner and what do you think about scientists? Do they like to just give up control, or do they like to take control of things? Okay, so you already know what I'm up against. So that's what I'm up against in this respect. The other aspect to that is, of course, you don't want scientists to be completely divorced from their data. You want them to understand how the telescope works, how the instruments work, what mistakes will be made during observing, what the capabilities are, what the characteristics of your detectors are, everything. So you do want them involved. If they never go to the telescope, that's hard to do. You have to have excellent communication between the observatory staff and the astronomers always, but particularly in the case where you're running a queue and they're not coming to the telescope. So I preach the queue observing, where we do everything in one block, but I'm also a big advocate for making sure that people, especially students, get the experience that they need by going to the telescope. So what does that mean? That means I drive a lot to the telescope to take students up. During the shutdown period, which is during the monsoon season here, we do lots of repairs and maintenance, upgrades to the instruments. But one of the unusual things that we do is that we have 2 mirrors, and every summer one of them gets washed with a mild detergent and distilled water, and the other one gets completely stripped of its aluminum coating and re-illuminized. And then the next summer they switch. So the one they illuminized the previous summer gets washed, and they strip the other one and recoat it. It's a big endeavor. It takes many weeks to do this, which is okay because the monsoon is kind of unpredictable. You never know when it's going to come back. So you have the time to do that. What I love about this picture is like the accidental Renaissance painting feel to it. So one of our volunteers, Paul Schultz, took this picture, and I really love it. And at that moment, we're stripping the aluminum coating off of one of the mirrors there. That's me on the side. So what kind of science do we do with the LBT? Well, like most telescopes, because we have so many partners, from so many institutions and so many different astronomers. We have lots and lots of topics that, especially these days, time domain science has become very important. So following up explosions of supernova, dying stars, gamma ray bursts, things that are happening very quickly on the sky that you need to respond to. So time domain science is becoming more and more prevalent, and we certainly have our fair share of that. But I wanted to share just a few results with you. This is a very recent result from a camera called Shark Viz. So where does that live on the telescope? That lives on the tertiary mirror, focuses the light into the middle of the telescope. It's located on one of those sides on the inside there. It's a visible light camera. It's fairly new. It's only been commissioned in the last year or so. And they decided to have a look at the moons of Jupiter. And in this case, it's the volcanic moon Io. I grew up saying Io. Lots of people say Io. I don't have a preference. What do you guys like? We'll use whatever you like. Io? Okay, we'll use that. So this is the Hubble Space Telescope image of this. And the LBT image is on the right. So that was taken in 3 filters, a few hours long, part of the commissioning of this instrument. And I find it really, really impressive that despite the fact that Hubble's above the atmosphere, we're able to, with our adaptive optics, get images that, you know, the resolution is noticeably better. So they also use some computer processing called deconvolution to sort of sharpen up the picture. And one of the interesting things that they found was that if you see a dark patch with a red ring around it, right, that this is an indication that the white patches are typically some sort of silicon feature, and the red patches are typically associated with some sort of iron feature. And the interesting thing about that is when they compared that new image from the LBT to the old image, an older image from Voyager and Galileo, they saw that there are new white and black patches on the surface. So in other words, that red ring feature, which was a known feature of the moon, is now sort of interrupted by a new explosion. So they're finding out about things that are taking place on the surface of the moon in real time. So very interesting for them. And this is being followed up because, of course, they want to keep looking at the surface as it changes. So we'll see this again. We've tried a couple of times and sort of got bitten by the weather lately, but we'll get back to it. Another recent from this year, actually, was a Nature paper by a postdoc at the University of Arizona, Jacob Isbell. They used what's called the LBT interferometer. Now, this lives in the center of the telescope, and it actually combines the light of both mirrors into one, as if you were using one 23-meter telescope. This is what they call a strategic instrument. That is, it was considered a specialty of the LBT and considered one of the most important science drivers for the LBT. So this is from the LBT interferometer. It is the highest resolution direct image of an active galactic nucleus. So this is a nearby galaxy, nearby spiral. Many massive nearby spiral galaxies tend to have black holes, massive black holes in the center of them. And associated with that black hole, there's some sort of active galactic nucleus, some sort of activity in the center. It can be in the form of rings or jets or outflows. And in the very center, using the super high resolution Large Binocular Telescope interferometer, they're taking a direct image of the very, very center of this galaxy where they believe there's a black hole and an associated activity. So these images were taken in the infrared, and they do confirm that there's a dusty wind, so some outflow from this central object that's generating shocks in the area and generating some sort of collimated jet of gas that's emanating from the center of the galaxy. These were expected, but never imaged in this way before, so this was an exciting new result. So I'm now going to show my bias by looking at more nearby galaxies, because that's what I'd like to study. This project is called LIGHTS, LBT Imaging of Galactic Halos and Tidal Structures. So they are looking at 20 to 25 nearby galaxies, which are similar to the Milky Way. Some of them are a little bit less massive, but not too far away from us, out of our local group, but still nearby. And this survey is headed by Dennis Zaritsky, who's a professor at the University of Arizona. So why do you want to look at nearby galaxies? So we typically have ideas about how galaxies form, but it's very difficult without simulations to try to image every little bit that we think might be happening over a long period of time. But it's almost certain that we're missing satellites to nearby galaxies, so smaller galaxies that are forming and interacting, or clouds of dust or clouds of gas. And the only way to get down to what is the real structure of the galaxy is basically to take as long exposures as you can of those nearby galaxies and try to really push the limit of what you can see around a nearby galaxy. So in this case, around just one or several of these galaxies, they found 54 other smaller galaxies, which are believed to be in the same vicinity, which are unknown before this. These types of images, if you're a numbers person, the surface brightness magnitude is like 32. It's unreal compared to sort of your normal picture that you might look at in a magazine of a galaxy. And the depth of the imaging for these objects exceeds what the Rubin Observatory will do over its entire 10-year lifespan. So Rubin is a survey telescope. It'll go over the same parts of the sky every single night. But even in 10 years, it wouldn't get as deep as these LBT images. These were taken with the prime focus camera, so the ones that just sit up on the top on the swing arms. So no adaptive optics or anything, just extremely deep imaging. And I just like this one so much, we'll just blow it up. And you can see how far the galaxy extends out in every direction, especially along its major axis. You can see faint rings of still star-forming regions with dust in them. This is an optical image taken in 3 bands, so it would be interesting to do it with the infrared, but I'm not sure we have the capabilities to do it that deeply. And you can see lots and lots of other previously unknown tiny galaxies, which are either in the background or they might be smaller galaxies that are orbiting this one. So I know I let my bias show, but that's okay. What is coming up in the future? So for the last couple of years, there's an instrument being built called iLocator. It's being built by principal investigators at Ohio State and Notre Dame universities. And it's expected to arrive at the LBT. It keeps being pushed back a little bit, but that's completely normal for an instrument. I'd be surprised if that didn't happen. But it'll undergo a review, so sort of a pre-processing review to make sure it's ready to arrive at the observatory, probably towards the end of the summer. And then it'll be shipped out and driven up to the mountain in pieces, essentially. And we're hoping that by, mid-fall, we'll be able to put this instrument on. And its whole purpose is to find, it's an ultra-high precision spectrometer, so its main focus is to find exoplanets around nearby stars, and stars that are generally cooler, smaller than our star. So should be very interesting to see if it can find planets. They're already doing things like getting data pipelines ready so that as soon as the data are processed, people can start looking at them. So we're very excited about that. We also realize that the LBT now and its instruments that were originally built are something like 20 years old, which to me doesn't sound that old anymore, but but in terms of technology, it's quite old. So there was a call for new instrument proposals to the community from the observatory. We received 13 ideas, so it's just a letter outlining the instrument that they would like to build and what kind of science they might want to do with it. Some of them are modifications to instruments that already exist. So there's one proposal, for instance, to replace all of the detectors in that large binocular camera on both sides that live at prime focus. So there's nothing wrong with the ones that we have now, right? I just showed you these beautiful galaxy images, but the technology is old enough that it takes a long time. You know, after you take an image, you have to read the image out, you know, all of the pixels out. In the older electronics, it just takes a long time to do that, you know, a couple of minutes. But, you know, in today's astronomy, you don't want to waste a couple of minutes on the sky while you're reading out. And you do that over and over, right? You do it every 5 minutes all night long. So you don't want to lose that time. But the newer detectors are easier to maintain. You don't have to use a lot of liquid nitrogen to keep them cooled. That's less burden on our staff. The detectors are more sensitive and they read out faster. So that's one of the many 13 proposals that we have. Some of them are completely new, brand new instruments. And so the puzzles pieces that you have to fit together are, how many instruments can your staff support? Because you only have so many people, and those instruments have to be taken care of, you know, several times a day, and repaired and maintained and improved over time. So you can only sort of have so many instruments to take care of. One is a space issue, right? It's a huge facility, but even so, with 13 new instruments, when you weren't using them, I don't know where you would put them. It's a space issue. It's like, you know, trying to fit 20 people into apartments. You know, you're not going to be able to do it. So the proposal for deadline for the full proposal, not just a letter outline, is at the end of May. And at that point, the board of the observatory and the science committee will need to get together to review them all and try to prioritize what science seems the most interesting. Do we need to retire some instruments in order to get more instruments? Will some just be completely replaced? So that will be a long discussion. Of course, the other factor is always, just because we called for proposals doesn't mean we're giving you any money. So anyone who's proposing for a new instrument will need to find their funding from outside sources. And how many of those will get funded? I don't know. I mean, last time I was on a National Science Foundation review panel, I think we were able to approve 3 of the 30-something proposals that we had. What is it going to be this year? -3? I don't know. So we'll see. So depending on all of those things sort of depends how we can move forward. But it's important to move forward, right? Because you need to keep improving the state of astronomy and the capabilities of the telescope if you want to stay on the forefront of the science. So, all right, are we going to talk about the elephant, I mean squirrel, in the room? So if you've lived in this area for a long time, you'll know LBT is actually has a very controversial past, and I'm probably not helping that, but this is one of the reasons. So the existence of the endangered red squirrel, they only live at high altitude, sort of above 9,500 to 10,000 feet. This is one of the reasons that the LBT is actually not built on Mount Graham itself. It's sort of built on an adjacent peak called Emerald Peak. And it's one of the best studied populations of animals anywhere in the world, because it has now been studied for more than 20 years, close to 30 years. And it turns out that the LBT is not really the issue for the squirrel. The issue for the squirrel is that it has noisy, invading neighbor squirrels of a different species that fight for the food. They're also very affected by drought and fire. So fire is the big one, right? It destroys the trees. And the population got down to 35 squirrels after the 2017 fire. And so the latest survey results, which I was really happy to hear, is that there's now 233 squirrels, up from 144 last year. So they seem to be on the rebound from that 2017 fire, which is great. And you can see it when you go up there in the landscape that, you know, things are slowly returning. So because of this, Mount Graham is a red squirrel refugium. So if you go up there You have to sign a piece of paper that says you will not harass the squirrels. And there are like 50 other, adjectives for not troubling the squirrel. I don't think I've seen one. I've seen squirrels there, but I'm not a biologist, so, I said, how do I know if I've seen a red squirrel on the way up? And my mentor at the telescope, John Hill, who's been there before it was even called the LBT, said, well, the red squirrel is a gray squirrel with a red back, and the gray squirrel is red squirrel with a gray back with a black stripe. And there are 3 types of chipmunks up there too. And I was like, so you're driving past and you're like, squirrel, but I don't know. I have no idea if I've seen one. Given that there are only 233, I'm going to go with no. I'm going to guess that most of what I have seen has been the other type. But it's fun to think about when you're on the way. Don't hit the squirrel with your car. That's like every time you see a squirrel on the road, you like slam the brakes on. Like, I cannot be the person who hit a squirrel. Here's some other fun things. So Mount Graham International Observatory, that's the site that LBT is located on. There are 2 other telescopes up there. LBT was not the first telescope. The first telescope was actually the Vatican Advanced Technology Telescope. It's a smaller telescope, and now mostly it's a survey telescope, so there are not as many people there as there used to be. They mostly observed remotely. There's also the submillimeter telescope, which was originally partnered by Germany, but is now run by the Arizona Radio Observatory. So, fun fact, originally, the LBT had 2 instruments built in Germany, which were called Lucifer. And they had absolutely nothing to do with the Vatican Observatory. Okay, here's the story that I was told. The story was that in the town in Germany where the Lucifer instruments were built, there was a mayor of that town, and the mayor's last name was something like devil in German. And they wanted, they were trying to curry favor with the mayor and the city council and etc. And so they playfully named the instrument Lucifer to sort of, tease the mayor a little bit about his last name. That's what I was told. However, if you Google Vatican Observatory and Lucifer, you will get a very different story. You will get some really extraordinary conspiracy theories about aliens and how the Vatican astronomers know all about them and have known about them or are keeping them all secret from you. And LBT is somehow involved in this. The latest one, and there is a trailer, and I was actually kind of tempted to bring it and play it for you, but I just can't. This is online too, so, and it's going to stay on YouTube forever, so I can't. But Aliens Uncovered Jesuit Secrets. That's the latest documentary about the involvement of Vatican Observatory. And the trailer itself is really hilarious, like all AI generated, and somehow there are Egyptian pyramids in it and everything. I don't know. So just for the record, those instruments aren't even called Lucifer anymore. They're called Lucies because the original instruments were supposed to have an integral field unit in them, and they ended up not doing that. It made the instrument overcomplicated and run over budget. So they're just called Lucy. It's not to get out of this. It's not to discourage conspiracy theorists, I promise. So outreach. So we are on land adjacent to the San Carlos and White Mountain Apache tribes. As the LBT Corporation has for some time tried to show its interest and support that community. There's a scholarship every year for students who attend the Eastern Arizona College who are from those reservations. And lots of other outreach that I'm doing. I just was going to list a few of the things that we have done recently. We recently did a tour for a large number of students who drove down from NAU. We told them they couldn't possibly drive down from NAU and go up to the telescope and come back down and go back to NAU in one day. So we convinced them to stay in Safford for the night. There are a couple of hotels, believe it or not, in Safford. And they stayed there, and then we met them in the morning and took them up to the telescope. They're all members of the astronomy club, but it was interesting. Almost none of them were astronomy majors, but they were all interested in being up there and learning more about it. Some of them were math majors or geology. Coming up in May, I have a documentary film company who would like to come up. No aliens or anything this time. Actually, what they're exploring something. I haven't quite wrapped my head around it, but they would like to focus on climate change and how people in this area, it will be too hot to function during the day, so everyone will become nocturnal. That's the idea they're exploring. And so this idea, I don't know, they would like to come up to the telescope and film people working at night. And so, which is okay, we can do that, but I hope they realize how cold it is on the mountain. It's not like, if you don't need to be nocturnal, you just need to go up to 10,000 feet, and that solves your issue, right, with the heat. But yeah, so I'll be taking them up there in May to show them around, and they'll be doing some filming. So you can keep your eyes and ears open for that upcoming documentary. Another interesting thing that was requested was there's a digital media master's degree student at the University of Edinburgh, and she is exploring the idea that people use music to cope with loneliness and homesickness at college or at observatories. And she wanted people to go to the telescope and talk about their favorite songs or play music. And I was like, I'm in, because I play the violin. So I went up yesterday and played the violin in the giant 2 by 8.5 meter telescope dome, and it echoes a lot, but it was kind of fun at the same time. So I'm going to be sending her clips of that, and that'll be another project that comes out soon. So you probably want to know if you can go and see it and find the aliens. I mean, see the telescope. So we do have tours. So they start in mid-May. They go through mid-November. It does require the permits. You have to sign that you're not going to harass the squirrels. So you do have to make reservations ahead of time. The good news is that the volunteers are extremely well trained. They actually go through a course at Eastern Arizona College so that they're prepared to, speak really well about the telescope, and they also have good first aid skills and all the things that you need to be a good tour guide. We have said now that, COVID has sort of, for a while there were no tours, obviously, but after that we're sort of ramping back up. And so they will have double the capacity for tours that they did last year, as long as they can get enough of those qualified volunteers to sign up for the course and be ready to go. So there should be more spots this coming season than there have been in the past, and hopefully that will help. They're always full, they always get full up. So, call early if you're interested in going, or, you know me now, right? We're all friends. So you can email me if they're all full, and we'll see what we can do for you. Okay, we do have a website. We are on Facebook. We are on X, although it's another conversation, but we are there if you want to reach us, and I'd be happy to take questions. I don't know about the microphone. Yes, Steve's got the microphone for you.